So, in order to continue with solving systems of equations, we need to take a pause for 2¼ days and learn a concept called matrix operations, dealing with matrices, because we're going to need that background in order to go on to Cramer's rule and go on to solving systems using matrices. Okay? So we need this background today, tomorrow, and the first part of class on Thursday in order to get to Cramer's rule and then eventually get to solving systems of equations by matrices. Okay? I think once you see matrices in action on Friday when you're solving systems of equations, I think that will become your preferred method of solving systems of equations because it is the least labor intensive, if you will, to do. So, but in order to get there, we have to back up and do some background stuff. There is a formative this week, Wednesday, in the Resource Center, okay? And your test is next week, Friday. Okay? So formative this week, test next week, Friday. Okay? So, a matrix is a rectangular arrangement of numbers organized into rows and columns. Okay? So, rectangular meaning that if there's 3 columns in the first row, there's got to be 3 columns in every row below that. Okay? If there's 2 columns in the first row, then there's got to be 2 columns for every row below that. Okay? So, rectangular in that manner. Okay? We name matrices using capital letters. Okay? So, this right here is matrix A. Okay? That is matrix A. And then this other stuff after it, that's the dimensions. Whoa, drop the pen. Okay? That's the dimensions then of it. So A is a 2x3 matrix because it has 2 rows and 3 columns. Rows are horizontal, columns are vertical. Okay? Each of those individual numbers are called elements. Okay? So matrix A has 6 elements that make up its matrix. Okay? Each element has an address. Okay? So for instance, the number 3 is located at A11 because it's in the first row and the first column. Okay? Now, some of you have one address, right? Some of you have multiple addresses. Okay? So we could have another 3 somewhere in our matrix. For instance, if I put the number 3 there instead of 0, then the element 3 would have 2 addresses. It would have address 11, and it would also have address 2, 2. Because it would be in the second row, second column. Okay? With me? Okay. each element has its own distinct address. Remember, if there's one thing that you take away, everything is in matrices is rows by columns. Okay? Dimensions are rows by columns. Tomorrow when we multiply, you're going to multiply the rows of the first one times the columns of the second one. Okay? It's always rows by columns. Addresses are given rows first, columns second, etc. Okay? There are only 3 mathematical operations that you can do with matrices, all right, of the basic 4. Okay? We can't divide. Okay? So today we're going to deal with adding and subtracting. We'll deal with scalar multiplication today, and then tomorrow we'll hardcore hit matrix multiplication. Okay? So, with that being said, it's very simple to add and subtract matrices. First, you've got to make a check. And that check is they must have the same dimensions. If the 2 matrices do not have the same dimensions, you cannot add or subtract them. Okay? Not possible would be your answer. Okay? If they are the same dimensions, then they are addable, and all you do is you add or subtract the corresponding elements. Okay. So, here we have a 2 by 2 matrix. Here we have a 2 by 2 matrix. Those dimensions are exactly the same, so I can add them. And I add the corresponding elements. So it would be 4 plus 2, 0 plus 7, negative 6 plus negative 1, and 2 plus negative 5. As a side note, I forgot to mention, matrices are brackets. If you don't put brackets, you're talking about something different, which we will get to on Thursday. Okay? So you've got to have the brackets with the, for lack of a better term, clause. Okay? These parts down here. Okay? You got to have the clause on your brackets. If they're just straight lines on the side, that means something totally different, and we'll learn about that on Thursday. Okay? So make sure you're getting into the habit of bracketing them. Okay? So this then becomes the matrix 6, 7, negative 7, negative 3. Questions on that? You can't go any further with it. I know. When you're adding and subtracting, your dimensions will be the same. Meaning the resultant matrix will be a 2 by 2 in this case. Okay? Or in this case down here for this one. 2 by 2 plus a 2 by 2 is going to give me a 2 by 2. Okay? Alright? Try this one. So then we got a 2 by 2, adding to a 2 by 2, same dimensions. So we have 3 minus negative 3, negative 5 minus 0, 10 minus negative 2, and negative 4 minus 4. So that gives me 6, negative 5, 12, negative 8. Okay. Questions on that one? Okay. Another style of problems that I have seen on your final. Okay, there's the last, or I shouldn't say last year. I don't know if this one made it onto the final, but the year before, one of these made it onto the final. So, possibility. Find the necessary value of x and y to make this matrix equation true. Okay. Well, if I were to take this left side of the equation here, well, then that would have to be negative 2 plus negative 3, x plus 7, 1 plus 6, and negative 5 plus 4, which would then become negative 5, positive 5, x plus 7, and negative 1. And then that would equal negative 5, y, negative 2, and negative 1. Okay. Now, the nice thing is that negative 5 is equal to negative 5. Negative 1 is equal to negative 1. Which then means that 5 is equal to y. Because if the matrices are equal, the corresponding elements have to be equal.
Mr. Lenz, would you get 5 out of 1 plus 6?
Yeah.
Oh, that should be 7. I'm sorry. Is that better? Okay. And then x plus 7 has to equal negative 2. So x has to be negative 9. A rectangular arrangement of numbers in rows and columns. It's a rectangular arrangement of numbers in rows and columns. Again, we have to go through this in order to get to where we can use them. Okay?
Will we have triple variable matrix? With like z, will we have a z in there too, like x, y, and z?
I could give you a w in there too. I could put a variable in each one of the elements. Yes. Yeah. Yeah. But that's different from what you're thinking of, like in solving a system of an ordered triple. Okay? Yeah. But yes, we will get to those using matrices too. But Joey, trust me, you want to know how to do matrices to do 3x3s. Yeah. It makes it so less labor intensive. You got to trust me. Okay? We're doing this for a reason. Okay? You got to trust me. Okay? Scalar multiplication is where we have a number in front of the matrix, And that number then gets distributed inside the matrix. Distribute. Now, this exact same problem could be written as this. Just so you know, the book likes to write these problems like this, where it gives you a list of matrices above a problem, okay? And then it would say, find negative 3a. Okay? Those are the exact same problems. Okay? In both cases, you're thinking the exact same thing. Okay? So you're going to take this negative 3 and you're going to distribute it in to every single one, all of the elements in that matrix. Not the first one, not the last one, every single one of them. If there's 12 elements in your matrix, you multiply by negative 3 12 times. Okay? Right? To every element. So then this becomes here 3 times negative 3, negative 2 times negative 3, 1 times negative 3, and negative 10 times negative 3. So that becomes then negative 9, positive 6, negative 3, positive 30. If you feel that you can get away without showing the top, you can get away without showing the top. Yep. I probably, after today, won't show the top anymore. But because this is new to us and people are confused because it's a rectangular arrangement of numbers and rows and columns, that you show it. Okay? Same question came up in the last class too. Yeah. No, it's I get it. It's something that you guys haven't seen before.
Well, I get what it is. I understand the shape of it.
It's hard. It's hard because I want to go to solving it too, and because solving it is so much easier with matrices than it is even with elimination and substitution and all that stuff.
Okay.
But we got to get this stuff before we can get to that stuff. Okay. Try that one. Still follows PEMDAS, yep. So you got to do the multiplication before you can do the subtraction. Okay. So first off, this one would become 8, 12, negative 4, 20. When you're reading matrices, left to right, top to bottom. Okay? It helps if you give the dimension first too. So here I would say, if I was reading this to you, I would say that it's a 2 by 2 matrix, 8, 12, negative 4, 20. So that you know when to jump to the next row. Okay? Then minus 6, negative 4, 1, 5 becomes 8 minus 6 is 2. 12 minus negative 4 is 16. Negative 4 minus 1 is negative 5. 20 minus 5 is 15. Questions on that one? So this first one would become 2, negative 3, 0, 1. This second one would become negative 6, 14, 2, negative 4. Both are 2 by 2 matrices, so both can be added together. So then that gets me 2 plus negative 6 is negative 4. Negative 3 plus 14 is 11. 0 plus 2 is 2. 1 plus negative 4 is negative 3.
Let's say one was a 2 by 3 and another one was 2 by 2.
Not possible.
Then it would have been not possible, and we wouldn't have had
Not no solution. Not possible.
not possible. So then we wouldn't have did any of the steps.
Correct.
That's not possible. Okay.
Correct. Okay. Try that one. Find me x and y.